All right, so welcome back to the next lecture. So we will continue to discuss about carbonyl compounds. And so as you may recall, in the previous several sessions we have been discussing about how to understand the reactivity of carbonyl compounds. And with respect to that, we sort of quickly realized that we are looking for the most reactive conformer. And so, as we discussed previously, there are several models that can help out in understanding the experimental outcome. One of the most successful models is the Falkenhahn model. And the Falkenhahn model, as shown here, gives us a fairly good understanding of how the reactivity of the conformer plays an important role. So the Falkenhahn model says that you draw out the carbonyl compound in the following manner, where you put the largest group perpendicular to the carbonyl group, and this will occur in two distinct conformations. And now if these are the most reactive conformers, then there are four approaches, and the approach that we looked at, we understood from the Bugge-Dunitz angle, was the nucleophile would approach between 105 to 107 degrees. And so of the four approaches, there's one that's more favored. And so if you pick that one and if you go ahead and draw the product that is formed, that will give you the major product. Okay, so it's a very good framework that helps us, sort of predict the outcome of the reaction. Now, in this Falkenhahn model, primarily sterics really important because the largest group being perpendicular to the carbonyl is dictated by sterics, and the more reactive conformer also, if you see here, we pick the most reactive conformer, or the trajectory with the lowest barrier is the one where the smallest group is present closest to the trajectory. And so sterics plays a dominant role. Okay, so the two important points in this model are sterics, and the second one is the Bugge-Dunitz angle. Okay, now there are other factors that can play a role in this carbonyl addition. In order to understand that, I'm going to change topics and go to SN2 reaction, and we will come back to the carbonyl addition shortly. Okay, so what we do is we do a simple experiment. So we take this chloride and react it with potassium iodide in acetone. The temperature is maintained at 50 degrees centigrade. Okay, and you all know that potassium iodide is a source of I minus. So I minus can certainly be, you can expect that I minus would attack over here and sort of kick out chloride. And the product that you would get is this iodide here and KCl. Okay, so this is perfectly fine. Now what I do is I measure the rate of the reaction, and the rate of the reaction is measured, and we just call this as 1 to be technically correct. We call this as a relative rate of the reaction, and we just assign it to be 1. Okay, now with respect to this rate, now what we do is we can do a systematic study about what happens if I change the group that is present next to the carbon chlorine bond. Okay, so here is the carbon chlorine bond, and so when we, for example, when we add a methyl group adjacent to it, so I start with isopropyl chloride, the rate of the reaction, or the relative rate of reaction, goes down to 0.02. Okay, so now this is a fairly substantial drop in the rate of the reaction, and the way we understand it is that when the carbon chlorine bond is being broken, so iodide attacks from at 180 degrees angle, and anything that sort of prevents or slows down the attack is going to slow down the reaction. So the way we understand this is that if you have additional groups over here, for example, then this is going to create a sort of a barrier for the attack to happen, and so therefore the energy, or the transition state energy, or the transition state is going to be achieved at a higher energy, and so the reaction rate is going to be slow. So this is fairly straightforward for us to understand. Now when I move from this chloride to allyl chloride, okay, so this is the allyl group, as many of you might know, and so when I move to allyl chloride, the rate actually goes up. Okay, and it goes up by about 79. Now, if I look at the structure of this compound and allyl chloride, there's actually not a huge difference in the sterics. Okay, so there's a double bond over here and there's no double bond here, and that's about it. Okay, but the rate increases by 79-fold. So that's very interesting. Even when I move from allyl chloride to benzyl chloride, the rate goes up even further up, and it goes up from 79 to 200, right? So now, in order to understand this, we sort of invoke the concept of orbital interaction. Okay, so here, as we have previously looked at in many cases, so if I look at the energy and reaction coordinate, and if I draw out the, let's say, the energy profile, right? So anything that stabilizes the transition state, which is going to lead to an acceleration in rate, is going to be favored, and anything that destabilizes the transition state is going to result in decreased rate. Okay, so what we understand from the experiment is that the rate of the reaction goes up by 79-fold. Okay, so therefore there must be some effect on the transition state of the reaction. So the way we understand it is that there's a pi bond next to this carbon. I mean, in this case it's Br that's shown here, but it's actually the carbon chlorine bond. So there's this p orbital which can interact with the bond that is being formed over here and the bond that is being broken over here, and that results in some stabilization in the transition state energy, and therefore the rate goes up. Okay, so the example in Claydon that describes this figure is with OR and BR, but you can very easily substitute BR with Cl and OR with I, and the same picture emerges. Okay, so therefore one can understand the acceleration and rate by invoking stabilization of the transition state by delocalization. Okay, with the allylic pi bond. Now going to the benzyl group, here also we find that the rate goes up further, and this rate, for example, in the benzene ring you have a complete aromatic ring that can actually interact with this, and so some level of extra stabilization is achieved by moving from allyl to benzyl, and therefore the rate goes up somewhat. So keep in mind the rate increase from here to here is only about twofold. Okay, so we have, this is approximately maybe around 80 to 100, and this is 200, right? So it's only about twofold. So it's not like a huge increase in rate. So it's not something that we would want to spend too much time on, but there is some level of stabilization of the transition state by the extended conjugation. But the most important experiment here is the following. When I do this experiment in the presence of benzoyl chloride, that is this chloride over here, I find that the rate of reaction goes up by 100,000. Okay, so this is 10 power 5 increase in rate of the reaction. So as you can imagine, this is a very, very large increase in rate, and we know that there's going to be some stabilization that can be afforded by the C double bond O, because that the C double bond O is going to have a 2p orbitals over here and so on. But yet it's not something that will completely explain the experimental outcome, because the rate of the reaction is going up substantially. So in order to understand this, what we propose is a model such as this. So when we look at this molecular orbital picture, we know that the C double bond O, if I look at the pi star of C double bond O, the pi star is there's going to be a smaller component from oxygen, and there's going to be a larger component from carbon. This is something that we have done previously in the course. Okay, and now if you imagine that this pi star is going to interact with this carbon bromine bond, or the orbital there, and here keep in mind we're looking at the antibonding orbital, which would be the sigma star, and so the sigma star orbital of the CBr bond is going to look like this, and whereas the sigma star of the CBr bond on the other side is going to look like this. But if you can propose, or if we propose that there is a combination of these antibonding orbitals, okay, so combination of the antibonding orbitals can result in a new orbital that is being formed over here, and this orbital is going to further more delocalized, and one can suggest that the nucleophilic attack happens much easier here when compared with the aliphatic bromide. Okay, so the idea here is that when the nucleophile attacks from at 180 degrees from this carbon bromine bond. But since we are looking at this combined, sort of more stabilized antibonding orbital over here, it's more facile. Okay, so therefore the carbonyl compound with an adjacent electronegative atom is a very special situation, and you can draw out an orbital picture such as this. So here is the pi star of the carbonyl compound, and here is the sigma star of the carbon X bond. And now when they combine, they produce a new orbital which is of substantially lower energy compared to the pi star and the sigma star. And therefore, its reactivity of the center goes up. That is, the reactivity of the center, as we know, is dictated by the energy level of the LUMO. And the energy level of the LUMO goes down because of the combination of the sigma star and pi star, leading to a new further stabilized antibonding orbital. Okay. So if I have to draw this picture a little differently, when the carbon-chlorine bond is perpendicular to the C double bond O. Okay, so keep in mind that this stabilization that we are suggesting happens when the carbon-bromine bond is perpendicular to the carbonyl. Okay, so as to maximize the orbital interaction. So when the carbon-chlorine bond is perpendicular to the C double bond O, then the attack which happens on this carbon here is going to happen at a much easier or in a much faster way, because this kind of arrangement is more reactive. So of the various conformations of this compound, this conformation is the more reactive conformation, and its rate is substantially, or rate of reaction is substantially higher than the other conformations. So this is how we understand the 10,000 or the 100,000 fold increase in rate of the nucleophilic substitution reaction. Okay, now when I go to the same picture, if I have a compound X, which is an electronegative atom, which does not leave, so this X is not a leaving group, how does this influence the reactivity of the carbonyl? Okay, so let's pause here for a minute and try to understand this, because this has a consequence on how reactive a particular conformer is when there's an electronegative atom adjacent to the carbonyl. Okay, so whatever we are proposing that increases the rate of the substitution at this carbon also will have an impact on the reactivity of the carbonyl. Okay, so when X is not a leaving group. All right, so let's assume that X is not a leaving group, then there's going to be still combination of the orbitals. There's still going to be a combination of sigma star and pi star, but instead of activating the carbon-chlorine bond or carbon-bromine bond as here, what it's going to do is it's going to activate the carbon also towards nucleophilic substitution. Now, if I want to look at it in terms of pictures, I've drawn it in the following way. So this is the pi star of the CO, which we are very familiar with by now. This is the sigma star of the CX bond, where there is a level of orbital here, and there's going to be a level of orbital, some amount of orbital here. And now when these two combine, they're going to produce a new set of orbitals, this combination of orbitals, which is going to be the new LUMO. Okay, so this is going to be the new LUMO. Okay, and as we saw with the previous case, the new LUMO is substantially lower in energy compared to the original LUMO that we had considered. So the way we would draw this picture is that if I consider the pi star of the carbon-oxygen bond, and if I consider the sigma star of the carbon X bond, where X is an electronegative atom, they both combine and they produce another orbital, which is a pi star plus sigma star, which is going to be substantially lower in energy. And this is going to be my new LUMO, or the more reactive LUMO. So what we are trying to tell you is that when you have an electronegative atom next to a carbonyl, okay, so the first situation that we looked at is when there is a carbonyl next to the electronegative atom, which happens to be a leaving group, then a particular conformation wherein the carbonyl is perpendicular to the carbon X bond substantially increases the rate of the reaction or makes that conformation much more reactive due to the appropriate combination of molecular orbitals. Or the way we understand it is that the appropriate combination of these orbitals produces a conformer that is going to be substantially more reactive. But now, when X is not a leaving group, the same combination of orbitals can occur for that particular conformation. And what we might expect is that that particular conformation is more reactive towards the nucleophilic addition reaction, which is what we are looking at when it comes to carbonyl compounds. So therefore, when X is an electronegative atom, which is not a leaving group, now what we can expect is that the nucleophile attacks the carbonyl, which is likely to occur, and the conformation wherein X is perpendicular to the carbonyl is going to be the most reactive conformation. So just to put this in perspective, the Felkenan model tells us is dictated by sterics, wherein the largest group is perpendicular to the carbonyl functional group, and that is what will tell us whether this is the conformation that is going to be the most reactive conformation, and essentially the conformation wherein the attack happens at 105 to 107 degrees, and this helps us predict the major product. But when there is an electronegative atom adjacent to the carbonyl, then the electronegative atom ends up at the position which is perpendicular, and the most reactive conformation is this, wherein the smallest group is now situated over here and the attack happens from here. So this effect of the electronegative atom has been given a name, and that's called the C-Plaque model. So the C-Plaque model emphasizes an alternative interaction between the orbital of the CX bond and the antibonding orbital to the nucleophile. Okay, so in this case, what happens is that the interaction between the CX bond and carbonyl group here produces the most reactive conformation, and the better the donor, the more electronegative X is, the better this interaction is and the more reactive that particular conformation is. Alright, so the C-Plaque model is basically suggests that an alternative interaction between the carbon X bond and the antibonding orbital is important, and that dictates the most reactive conformation wherein the nucleophile can approach. Okay, now in order to understand this, let's look at an example. So the first example that we are looking at is if I take this compound, which is shown here, and I react this with sodium borohydride, the major product that I get here is the following compound. Okay, now so sodium borohydride is basically a source of H minus, as all of you know, and so H minus is going to attack and then form an alcohol. Okay, so now in order to make things sort of clear, let's first assign the stereochemistry for this compound, and so that we can find out whether the model predicts the outcome correctly or not. And so the way I would assign the stereochemistry is I would label this as 1, and this carbon as 2, and this carbon as 3, and the hydrogen is actually over here, and so this would be S. Okay, and similarly if I assign the stereochemistry for the other chiral center, I get S, and so therefore it is 1S, 2S methyl thiobutanol. And now let's move to the model. So the model tells us that for the conformation, the C double bond O and let's say the electronegative atom. So the electronegative atom, or the atom with the lone pair of electrons here, is sulfur, and so sulfur is going to be perpendicular, and then you have the other groups, which could be the large group and small group and so on over here. Okay, so the key assumption in this is that the C double bond O is perpendicular to the electronegative atom. So based on this, we can draw out a conformation like this, where this hydrogen is here, this ethyl is here, and the phenyl group is here. I would urge all of you to go back and draw this out by yourselves. And so when I do a rotation across this carbon-carbon bond, then essentially I have these two conformations. And this model tells us that these are the most reactive conformations. Okay, so therefore the barrier towards reaction of these two conformers is going to be the lowest. And now in these two situations, there are, again, as we know, there are four approaches. And so the approach wherein the smallest group here is hydrogen and the next largest group is ethyl. And so this approach from here is going to be the most favored approach. So if I go ahead and draw out the product that is formed, now once this approaches, we know that the C double bond O is going to break, the OH is going to end up here, and the phenyl ring is going to end up here. So that's where this is written out. Okay, and the hydrogen which comes in, or hydride which comes in, is here. Okay, now if I assign the stereochemistry over here, what I will find is I actually get the SS configuration. So with this in mind, we can try and understand, or we can try and predict the product that is formed, as long as we know that the atom has a lone pair of electrons, and if it's electronegative, then the model that needs to be applied is this. If there is no such situation, then we are going to apply the regular Felkin-Hahn model and predict the product that is going to be formed. Now let's look at one more example wherein we have this kind of a group. This is NBN2, which is actually nothing but nitrogen with two benzyl groups. Okay, a benzyl group is this as shown here, and so the nitrogen with two benzyl group is actually has a lone pair on the nitrogen, and so this is the compound. And what we do is we react this carbonyl compound with, let's say, methyl lithium or ethyl lithium or some organolithium compound, and we end up with this product. Okay, now let's see whether our model is able to predict the correct stereochemistry. So the model here is that the C double bond O has to be perpendicular to the most electronegative atom, which happens to be this nitrogen over here, and this nitrogen's lone pair is going to interact with the C double bond O, okay, and increase the reactivity. So among the two conformations, we find that this, the one with the yellow drawn here, this trajectory is the most favored, and therefore we would predict that the attack would happen, or this is the most reactive conformation, and the attack would happen from here. And again, what we're looking at is the nucleophile, which is R minus. Okay, and when R minus attacks here, the OH ends up going here and the hydrogen ends up going here, and so the carbon R bond is going to be formed over here. Okay, now the way we would check it is to assign the absolute stereochemistry, which I have done here. So when I assign the absolute stereochemistry for this compound, what I find is that, this gets priority number 1, the carbon behind gets priority number 2, R gets priority number 3. So 1, 2, and 3. Hydrogen is number 4. So if I look from here, the hydrogen is far away from me, and so it is actually 1, 2, 3. It is clockwise, so therefore it would be R. Okay, and now if I redraw this, which is the structure that has been given to us, the stereochemistry that has been assigned here is also R, and so therefore the model that we have proposed is actually working.